Hi, you guys. This is Jerry Pinter. Welcome to Chapter 4, Part 3 on frequency response and the convolution property. So let's start out by sort of doing a little bit of review from Chapter 3. And this is the Fourier Transform and its relation to frequency response. So back in Chapter 3 and even Chapter 2, remember we defined the impulse response, h of t, little h of t, as the output of the system when we put an impulse or a delta function into the system. We also learned in Chapter 3 that if we put a frequency component as represented by this complex exponential, e to the j omega t, that has a frequency of omega, if we put that into our system, we found that the output of the system is given by the same signal as the input, e to the j omega t, but it's been modified by this function of frequency, which is called the frequency response. And we designated the frequency response uppercase h of j omega. Now we can see why we're using the letter h here for frequency response. Back in Chapter 3, we defined the frequency response, h of j omega, as this integral shown right here. But we can now see, now that we're in Chapter 4, that this integral is the definition of a Fourier transform. In fact, it's the Fourier transform of little h of t, which is the impulse response. So here we see the formal relation between impulse response, h of t, and frequency response, h of j omega. They are related by the Fourier transform. So the frequency response of a system is equal to the Fourier transform of the impulse response of the system, h of t. So that's why we use, little h here for impulse response, and when we go to Fourier transform, we go to the uppercase letter h here. Let's go ahead and start with an example here of calculating the frequency response. And actually, this example is nothing new. We did this back in Chapter 3, but now we can use our new lingo or language of talking about Fourier transforms. So suppose we have an LTI system here, and the impulse response of this system is given as h of t is equal to e to the minus t times u of t. So this is, again, a decaying exponential function, and our goal is to find the frequency response, h of j omega, of the system. Well, we can go ahead and do the integral like we did in Chapter 3, but a shortcut here is let's just use the results that we've got from this chapter. Back in Part 1 of Chapter 4, we found this important result here. It says that for an exponential function, x of t, for example, is equal to e to the minus at times a step function, then the Fourier transform, big X of j omega, is just 1 over a plus j omega, where a, this number here, is the number that's up here in the exponent. So this is the Fourier transform pair for an exponential function. Obviously, our impulse response here is an exponential function with a is equal to 1, so we can immediately just write our frequency response as h of j omega is equal to 1 over 1 plus j omega. Notice the 1 right here. That 1 is because this a here is equal to 1 up here in the exponent. There's no number in front of the t except for the minus sign, of course. Okay, so what this tells us then is that for our system, this particular system, if we have e to the j omega t going in, then what we have coming out is also e to the j omega t, but it's multiplied by the frequency response, which is 1 over 1 plus j omega. So this frequency response basically modifies the input of this system. All right, it modifies its magnitude and its phase, but the same frequency that goes in, which is omega, is the frequency here that comes out. but the phase and the magnitude are changed. So the frequency response, h of j omega, we can look at it here. It's obviously a complex function because it has that j in there. So we can gain insight into it by plotting its magnitude and phase. And again, this is something you did back in homework number 1. I believe it was the last problem in homework number 1. You were asked to plot the magnitude and phase of this particular function right here, and it looks something like this. This is the magnitude plot, and this is the phase plot. We'll talk a little bit more and discuss the meaning of this shortly. So let's look at the interpretation of the frequency response. What does it mean, and what does it really tell us? So, again, in the time domain, we've got a system where, if we send in a delta function or an impulse, as shown here, then the system spits out some impulse response, h of t. And for this particular example on the last slide, the impulse response was given to us as e to the minus t times the step function. So the impulse response looks like this. And we figured out the frequency response. The frequency response was this function here, which we determined on the last slide. Now, if we plot the magnitude of this frequency response, all right, that's shown right here. And again, this is what you guys did in homework number 1, so this is nothing new here. But if we plot it, it looks like this. So what does this really tell us? Well, the frequency response is telling us how the system behaves at different input frequencies. So this particular system, shown right here, passes low frequencies and blocks high frequencies. Now, how do we know that? Well, look at the frequency response plot here. At frequencies close to 0 here, notice the frequency response is a value of 1. That means all this stuff here in the parentheses has a value close to 1. So in other words, this system takes whatever low frequency input is going in, and the same input comes out. It doesn't change low frequency inputs. On the other hand, look what happens at high frequencies, way out here. The frequency response goes to 0. So that means this system is going to basically multiply the input signal by something very close to 0. So it's basically going to kill any signal coming in that has high frequency. So this is, of course, the definition of a low-pass filter. This particular system here is passing low frequencies and it's blocking high frequencies, and that, by definition, is a low-pass filter. Let's now turn to perhaps the most important and powerful property of the Fourier transform, and that is the convolution property. So the convolution property is great news for us, because what it tells us is that, remember, in the time domain, when we want to figure out what the output of a system is for any given input x of t, remember that the output is equal to the input convolution operation with the impulse response. Okay, so remember this star here means we have to perform a convolution of x and h. And this is, what we did back in chapter 2. And I don't need to remind you guys that it was not fun, right? It was tedious and very difficult. It was complicated to figure out the convolution of an input and an impulse response. Even for some of the more simplest of cases, we still had to do a lot of work to figure out the output. Well, the good news now is that we can work in the frequency domain using the Fourier transform, and look what happens. In the frequency domain, our input, x of t, becomes x of j omega. This is the Fourier transform of the input. The output in the frequency domain, which is y of j omega, is equal to x of j omega multiplied by h of j omega, which is the frequency response. In other words, all we have to do in the frequency domain is multiply the Fourier transform of x times the Fourier transform of the impulse response, which of course is called the frequency response, big H of j omega. Notice there is no convolution here at all. So we can figure out the output of a system now without having to do convolutions. So this is, obviously major progress for us to be able to avoid convolution. So the convolution property of the Fourier transform says that in the time domain, if y is equal to x convolution with h, then in the frequency domain, big Y is equal to big X times big H. And in general, any two signals, A and B, which have convolution in time, in the frequency domain, we just multiply their Fourier transforms, A and B, together. So, you know, this is, again, major news for us. It's going to make finding the output of a system much easier because we don't have to do convolution. So we'll look at that. In particular, we'll use this property in the next video where we analyze systems using some of these methods. There's a couple ways to prove the convolution property. The more formal way, I believe, is shown in your book, and you're welcome to follow through the steps there. This is just sort of my kind of back of the envelope informal proof of the convolution property. It's granted it's not probably completely rigorous, but it sort of shows of how you can do it quite easily. In the time domain, remember that a delta function that goes into a system produces h of t, which is the impulse response. So if we take the Fourier transform of this input, so basically we're going to the frequency domain now. So remember, the Fourier transform of a delta function is just 1. And of course, the Fourier transform of h of t is h of j omega, which is the frequency response of the system. Then if we multiply both sides by this function, this is not a function of time, this is a function of frequency, x of j omega, we get a result over here, which is basically the convolution property. Notice there's no convolution here, this is just multiplication of x and h. So whereas, you know, this is not a formal proof, it kind of gives us an indication of what's happening when we go from time domain to frequency domain. This brings up another example of the dual properties when we go back and forth between time domain and frequency domain. We've seen this, you know, in the last chapter, or actually last couple of chapters now. We've seen sort of a symmetry when we go back and forth. And we see this now with convolution and multiplication. So what we just showed was that the convolution property says that in time, in the time domain, when we do a convolution between A and B, when we go to the frequency domain, we just multiply the Fourier transforms of A and B together, okay? But it turns out that the sort of the converse is also true, and this is technically called the multiplication property. So in the time domain, if we multiply two signals together, in other words, signal A of t multiplied by signal B of t, then look what we get in the frequency domain. We have to do a convolution of the Fourier transforms of A and B. And then there's also a factor of 1 over 2 pi. But notice that, you know, here, up here, convolution is on the left and multiplication is on the right. But if we do multiplication on the left, we get convolution on the right. And this is, again, one of those properties of the symmetry of the Fourier transform and the inverse Fourier transform. And this property here, we're not going to see this for a little while in the course, but this multiplication property will become important when we do sampling theory in Chapter 7 and communication system theory in Chapter 8. Okay, so let's now turn to some examples of using the convolution property. Our first application is the cascade of 2 or more serial LTI systems. So look at this system here. We've got system 1, or really this is like a subsystem here, connected in series with system 2 here. So suppose system 1 has some impulse response h1 of t, and then system 2 has an impulse response h2 of t. So we know that the signal coming out of system 1, which we'll call y1, is equal to the convolution of x and h1, or remember h1 is this system's impulse response here. The signal coming out of system 2 is the input, which is y1, convolution with h2, which is this system's impulse response, right? And this is something that we saw back in chapter 2. This is nothing new to us here. But remember, y1, which is shown right here, is the convolution of x and h1. So in other words, the output of this entire system is x convolution with h1, convolution with h2. Well, now what we can do is use the convolution property and go to the frequency domain. And this y2 here becomes big Y2, all right, uppercase Y2, which is the transform of Y2. And all this over here, x, h1, h2, we can just multiply the Fourier transforms together. So we get big X1 times big H1 times big H2. These are all, of course, Fourier transforms and, functions of frequency, not of time. So what this tells us now is that if we have two systems in series like this, then we can combine these systems by simply multiplying their frequency responses together. So this is an example of system simplification. We start with two systems in series, and we can just sort of summarize it or reduce the system to a single system that has a frequency response given by the products of H1 and H2. Now we can take this one step further and show that the order of serial systems doesn't matter. So what we just saw in the last slide was, here we have system 1 first and then going into system 2. So the first thing we can do is combine these by multiplying H1 here times H2 here. But since this is just multiplication doesn't matter which one we multiply first. In other words, multiplication is a commutative property. So H1 times H2 is the same as H2 times H1, and now we can kind of go in reverse and split these back apart, and therefore we can put system 2 prior to system 1. So what this has just shown is that for systems that are in series like this or cascade architecture, it doesn't matter which system comes first. You can swap the order of the systems and the overall result is exactly the same. So here's an activity example for you guys to do. Let's see what we've got here. It says a signal x of t with a Fourier transform x of j omega, which is shown down here, is passed through a filter with frequency response h of j omega as shown. So here's the block diagram of our system. We've got a filter here, all right, and the filter's frequency response h of j omega is plotted right here, all right, down here. And the signal that's going in here has a Fourier transform given by x of j omega, which is shown here. So in this activity, you're supposed to do two things here. First of all, determine what type of filter is this. In other words, is it a low pass, a high pass, etc. And then part 2, make a sketch of the output signal's transform, y of j omega. In other words, what comes out of this filter, and you don't have to do it at y of t, but figure out what y of j omega, in other words, what is the frequency domain output of this system. So go ahead and pause the video here and see if you can work out these this activity here. So here are the solutions to the activity. The first thing it asked was, what type of filter is this? Well, this is by looking at the frequency response of the filter. We can see this is a band pass filter. Obviously, the pass band here is between the frequencies A and B, because the filter is just going to multiply the input here by 1. In other words, it's going to perfectly pass any frequency between A and B, but it's going to block any other frequencies. So frequencies less than A or greater than B, notice the filter has a frequency response of 0, which means it will block those frequencies. So what we do is we just take our input transform here, x, and multiply it by the frequency response, h, because remember the output here, y of j omega, is equal to x of j omega multiplied by h of j omega. So if we think of like overlaying these two spectrums, these two Fourier transforms on top of each other, we can see that the output is going to basically just be whatever is here between A and B, because that's the pass band of the filter. So this is the output right here. Notice everything outside of, you know, A and B here, this region, everything else has been blocked. So this big hump here has been blocked, and this smaller hump outside of B has also been blocked. This is, of course, what a bandpass filter does. Here's another activity for you to practice with. This one, you're asked to find the overall frequency response of the system shown. So here's a system right here, and you're asked to basically simplify this system so that it's just one functional block here. In other words, what is the frequency response of this overall system that we could put inside this box? So again, please pause the video and see if you can figure out the answer here. All right, so the way to figure this one out is we can combine system 2 and system 3 first. Remember that for subsystems in series, we simply multiply H2 and H3 together. And then, since that is in parallel with system H1, for a parallel system, we have to add the frequency response of H1 to the product of H2 and H3. So this is the overall frequency response of this system shown up here after it's been simplified. So that is the end of this video. This was part 3 from chapter 4. We have one more part of this chapter which we will get to next. Until then, I'll see you later. Goodbye.